Section 2.3 is called homogeneous equations with constant coefficients. All right, so what does that mean? What does it mean to be a homogeneous equation?
Equals zero.
Means it equals zero. What does it mean to have constant coefficients?
You have C's that are constant.
Arbitrary.
Not variables.
Not variables. All right, so for example, y double prime minus 4y prime minus 12 equals 0. That's a homogeneous equation with constant coefficients where x, y double prime, that's a 12y there by the way, minus 4y prime minus 12y equals 0 is not a homogeneous equation with constant coefficients. How come that one doesn't have constant coefficients? Because it's got a variable right there. That's correct. So, we did this back in section 2.1. How did we solve a second order homogeneous equation that had constant coefficients?
We use the y's, C1 y1 plus C2 y2 on the C's.
And how did we come up with that y1 and that y2 that we needed?
It was given.
We created something called the characteristic polynomial. And so what we did is we made a guess that the solution was going to look like e to the rx, and we took the derivative, we took the second derivative, and we plugged that all in. And what we saw is we ended up with a polynomial that we needed to solve, and that polynomial we called the characteristic polynomial, or the characteristic equation. Because when you plug these in, you get r squared e to the rx minus 4r e to the rx minus 12 e to the rx equals 0. And then what could you do? You could factor out the e to the rx, and then you could actually divide by e to the rx, because e to the rx can never be the number 0. And so we ended up having to solve a polynomial equation. R squared minus 4r minus 12 equals 0. And this has a name. This is called the characteristic polynomial, or the characteristic equation. And we like that very much because that's a quadratic equation. We know lots and lots of things about solving quadratic equations. How would you solve that?
Calculator.
Calculator would be one way. This one factors easily enough. This is r minus 6, r plus 2 equals 0. And so we end up with two linearly independent solutions. y1 is e to the 6x, and y2 is e to the negative 2x. And so our general solution is y equals c1 e to the 6x plus c2 e to the negative 2x. Well, here's the good news. The good news is not only does that technique work for second order differential equations, it also works for third order differential equations, fourth order differential equations. So let's say I give you y triple prime. Oh, we can't do this yet. All right, we got to talk about repeated roots and complex roots first. Then we'll talk about third order differential equations. All right, we talked about repeated roots the other day. So these you might end up sometimes with your equation. Let's say you had y double prime minus 4y prime minus plus 4y equals 0. You compute your characteristic polynomial, r squared minus 4r minus 4 equals 0. Plus 4? No. It factors. it factors as r minus 2 squared equals 0. So you only get one solution, r equals 2. What happens when you have repeated roots? What's your other solution? Our y1 is e to the 2x. What was our technique for the other solution? X, e to the 2x.
And those be like y1 can be x e to the 2x. What is that?
Well, remember, again, our technique was we made a guess that y was e to the rx.
Oh, okay.
And then we solved, we came all the way down here, we discovered that r was the number 2, which means one answer is e to the 2x. But then we need a second linearly independent solution. And what we saw back in section 2.1 is if you simply multiply by x, take this, take the derivative, take the second derivative, plug it all in, it'll happen to work.
Can you slide that up a little bit?
Slide that a little that way. Okay? General solution, therefore, is y equals c1 e to the 2x plus c2 x e to the 2x. So what do you think you would do if your characteristic polynomial turned out to factor as r minus 2 whole thing cubed? Well, first off, if it factors as something cubed, what kind of equation did that come from in the first place? It came from a cubic. It came from a third order homogeneous equation. So how many answers do you need? Three. So one of the answers is y1 equals, not 2, e to the 2x. So there's one solution. I need two more. X e to the 2x would be another one. And the next solution would be you multiply by x again. There would be your three solutions. So there's what you do when you have repeated roots. You have repeated roots. If your root repeats 3 times, you take your solution, you multiply by x, you multiply by x squared. If your root repeated 5 times, you'd have your solution, multiply by x, x squared, x cubed, x to the 4th. So on and so forth. Okay, questions on that? All right, now we need to talk about complex solutions. What do you do? Because sometimes when you solve quadratic equations, you do get complex answers. All right, does anybody remember your fun days in Calc 2 when we talked about series expansions of functions?
Like you're trying to graph.
Of course you do, very good. So what's the series expansion for e to the x?
Wasn't it the series expansion of sine of x plus cosine of x with the difference of imaginary number? Or was that something else?
You're close. What I was just looking for was e to the x. Our series expansion was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and I continue on forever. All right, so many, many years ago, Leonard Euler took that expansion and he decided to plug in a complex number. He decided to plug in e to the I theta. And he ended up with 1 plus I theta plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial, plus it goes on and on forever. Well, that's 1 plus I theta plus. What happens when you take I and you square it? What's I squared? Negative 1. So this one becomes negative theta squared over 2 factorial. But the I is completely gone, isn't it? I squared was just negative 1. Plus, what's I cubed? I cubed is negative I. So this one is negative I theta cubed over 3 factorial. Plus, what's I to the 4th? I to the 4th is 1. So this is theta to the 4th over 5 factorial. 4 factorial I meant. And I'm going to do 1 or 2 more. Plus, what happens when you take I to the 5th? It becomes I to the 1st, doesn't it? Because I to the 5th is I times I to the 4th, and we just said I to the 4th is 1. So that becomes I theta to the 5th over 5 factorial. What's the next one? What's I to the 6th? It's negative 1. So you get negative theta to the 6th over 6 factorial plus on and on and it goes forever. So notice what's happening. On every other one, we have an I. Starting with the first one, you have just a number, and then there's no I, and then there's no I, and then there's no I. All right, so what I'm going to do is I'm going to change order here. So I'm going to put all the terms together that don't have i's in them. So that's 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial plus, and those would go on forever. And then plus all the ones that have an I in them. The ones that had an I in them were just theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial plus, and they go on and on forever. Better? All right, so does anybody remember the famous expansion that starts with 1 and then it has even powers but goes minus plus minus plus? Close.
Cosine.
Cosine. This one happens to be the expansion for cosine. And the one that starts with the odd powers and goes minus plus minus plus, that's the expansion for sine. So this is cosine of theta plus I sine of theta. If I add all these up, all of these as one block, all added together, is the cosine series. In the second block, all of these, I could write them in summation notation, but if I add them all up, that turns out to be sine. Okay, so that's Euler's famous formula. Here's Euler's most famous equation. What happens if I use theta to be pi? Cosine of pi is negative 1. Sine of pi is 0. So this formula is usually written in the form e to the I pi plus 1 equals 0. And Euler claimed that that was the perfect formula.
What makes it perfect?
What makes it perfect? It has all 4 important numbers in it. The 4 important numbers are 0, 1, e, and pi. And it also happens to have I in it, the complex number. So as far as Euler was concerned, that was the most perfect formula that could ever be developed. But it is interesting that the numbers 0, 1, e, and pi show up all the time in all sorts of weird places where you would never expect them to show up. So I think that's why he thought it was so important.
Especially E. He's just kind of like, oh yeah, by the way, here I am.
And pi just jumps in every now and then too. All right, so for our purposes, the important thing is, if you have e to the a plus bi. So let's say you solve your characteristic polynomial and you end up with a quadratic equation that has complex roots. This can be written as e to the a times e to the bi. So that's going to be e to the a times what we just proved is that this is cosine b plus I sine b. It's not me this time.
Somebody's really trying to reach somebody.
What does that tell you? How many solutions did you just come up with? 2. You have e to the b times cosine, that's one solution. And then you have e to the a times sine, that's a second solution. Are those two solutions linearly independent? Can I take e to the a cosine, multiply it by a number, and get e to the a sine? No, I can't. So there's your two linearly independent solutions. Took so much to get there. But now once we have it, things get easy. So for example, let's say I want to solve y double prime plus 4y equals 0. I compute my characteristic polynomial. My characteristic polynomial is r squared plus 4 equals 0. And that has complex roots. The answers are r equals plus and minus 2i. In this case, a, this a here that we're talking about, a is the number 0. A is the number 0. So this e to the 0 is going to be just 1. So our solution is y equals, we're going to have c1 cosine 2x plus c2 sine 2x. Where does the 2x come from? Notice that b here is the number 2. So there's b is the number 2. So there's the number 2. And then we need it to be a function involving x, right? So 2x.
We just like,
Is there supposed to be an I between the C1 and the C2? Excellent question.
well, it's imaginary, so it doesn't.
My C2 might now be an imaginary number.
Well, that's fine.
So we don't bother writing the I. We accept the fact that C2 might be an imaginary number,
We want to know that.
and we're okay with that.
We're okay with that.
Okay. Other questions? All right, now let's look at one of these ones that I wanted to do before. I was all excited about. Y 2y triple prime minus y double prime minus 5y prime minus 2y equals 0. I write down my characteristic polynomial. My characteristic polynomial is 2r cubed minus r squared minus 5r minus 2 equals 0. How do you solve that equation? All right, typically when you have 4 pieces, 1, 2, 3, 4, you do factor by grouping. Unfortunately, factor by grouping does not work in this problem. Because, think ahead a little bit, What's the common term in the first group?
R squared.
R squared, and you're going to be left with 2r minus 1. What's the common term in the second group? So you're going to have minus 5r minus 2. Is there anything common between those two things that you just had? No, unfortunately. So factor by grouping typically isn't going to work. So how do you solve it?
Calculator.
You grab your calculator. Wonderful idea. Y equals 2x cubed minus x squared minus 5x minus 2. So I type that into my calculator. I draw myself a pretty little graph. Okay? So where are the answers?
Second, all in place.
It looks like there's one here,
There's 3.
and it looks like there's one there and one there.
Yeah.
And there should be 3 answers, right? We want there to be 3 answers. How do you find those 3 answers?
Second trace. When you go zoom box.
Second trace,
Then you go 0.
find the 0. I'll find this one over here first. That one's x equals 2.
What did you hit to get rid
I went like this. I went second calculate, and then I went down to the 0.
Okay, thanks.
Now this, finding these two might be a little tricky. I might have to zoom, because I got to get, if I'm looking for this one right here, I've got to get somewhere left of it, so I want to be right up there. Let's see if I can get the cursor right up there. Looks like I can. Move over there, make a guess. R equals -1/2. And then the third answer looks like it's -1. And it is. If I plug in -1, I get 0. So there's our 3 answers. So the general solution of this equation is y equals c1 e to the 2x plus c2 e to the -1/2x plus c3 e to the -x. Questions on that one? All right, let's try another one. That's not what I wanted to have happen. Let's try the fourth derivative of y minus the third derivative of y plus the second derivative of y minus 3 times the first derivative of y minus 6y is 0.
Do the form with the R's.
All right, so I write down my characteristic polynomial. That's r to the 4th minus r cubed plus r squared minus 3r minus 6 equals 0. How do you solve a 4th degree polynomial?
Calculator.
Calculator, all right. X to the 4th minus x cubed plus x squared minus 3x minus 6. How many answers should I find?
4.
4. How many answers do I see? 2. Where are the other 2?
Invisible.
They are invisible because they are imaginary. All right, so we find the 2 answers. The 2 answers look to be 2 and -1. Let's just check real quickly. The easy way to check is to plug in 2. It is a 0. Plug in -1. It is a 0. So we know two answers. R equals 2. R equals negative 1. How do you find the two complex answers?
We don't just incorporate them into the.
We don't know. We do. We do. All right. Well, what does it mean to say R equals 2 is an answer? What that means is R to the fourth minus R cubed plus R squared minus 3R minus 6. It has to factor. It has to factor. There has to be an R minus 2 in there. Right? So for 2 to be an answer, I have to have an R minus 2. What has to happen for negative 1 to be an answer?
It has to be R plus 1.
There has to be an R plus 1. And then what's left over? It has to be something with an R squared, doesn't it? Because if I FOIL these two out, that's going to give me an R squared. So I need something that has an R to the fourth. So the question is, how do we find that quadratic polynomial that's left over?
Long division.
You can do long division or you can do synthetic division. Those are your two choices. Anybody remember long division or synthetic division?
I think I remember something. Maybe.
Which one do you recommend?
I recommend synthetic because I think it's faster and easier. Let's do that. Okay, so the way synthetic division works, you write down the coefficients. So I'm going to write down 1, negative 1, 1, negative 3, negative 6. And then we draw an upside down division sign. And then since R minus 2 is an answer, we write a 2 right there. Does this look familiar to anybody? Anybody know what to do next?
Yeah, you bring the 1 down.
This first 1 comes straight down. Then what do?
Multiply.
You multiply 2 times 1?
2.
2, and you write that right there.
And you add, right?
And then you add. Negative 1 plus 2 is
1.
1. And you continue with that process across. You multiply again. 2 times 1.
2.
2. You add. 1 plus 2.
3.
3. You multiply. 2 times 3. 6. You add. 3. You multiply. 2 times 3. 6. They add up to 0. If you did it right, the last one should always be 0. Why should the last one always be 0?
No remainder.
That's your remainder. The last number would give you your remainder. So what we've just shown is that R to the fourth minus R cubed plus R squared minus 3R minus 6 factors as R minus 2 times R cubed plus R squared plus 3R plus 3. So that's what dividing by the R minus 2 did. But that's not really what we want to do. What we really want to do now is divide again and divide by the R plus 1. So we divide by a negative 1. So we start with these numbers that we have written here. 1, 1, 3, 3. And we divide again using a negative 1. Oh, I'm running out of time in a hurry here. All right, so I bring down the 1. I multiply. Negative 1 times 1. Negative 1, I add. 0. Negative 1 plus 0. Or negative 1 times 0 is 0. Add, I get a 3. Negative 1 times 3. Negative 3, that's a 0. So I'm left with R squared plus 3. What are the solutions to R squared plus 3? Plus and minus, not 3i. Something else I.
Yeah.
I. So there are our other two answers. R equals plus and minus I square roots of 3. Once you have an I in there, what does that tell you? That tells you you have complex roots, which tells you you're going to get a sine and a cosine. Answer to this equation is y equals, I have a c1 e to the 2x. I have a c2 e to the negative x. And then I'm going to have a plus C3 cosine square root of 3x plus a C4 cosine or sine square root of 3x. Questions on that?